Okay.
So I'll share my screen again, right?
Yeah, whenever you're ready. It's a great pleasure to have Kevin Costello visiting virtually to give us this seminar. I won't go into elaborate introductions. You're known to everyone here.
Okay.
Thank you very much. You're going to tell us about twisted holography. Okay.
Yeah,
Please. Oh, I should mute. I forgot to mute everyone, just to get on the safe side and mute all. You can unmute yourself, Kevin. Let's see. Oh, I'll unmute you. Okay, just in case.
There we go.
Can
you hear me now?
Yeah.
Okay. Yeah, thanks very much, Benjo, for inviting me to give this talk. It's a great pleasure to talk to the Irish mathematical physics community. So what I want to talk about is an approach to holography that has been developed over the past couple of years, which is based on this mathematical notion of Koszul duality. So I'll get to that in a minute. So what I'm going to talk about is based on these papers, and if you want to read something about it, you could, for instance, look at this paper I wrote with Natalie Piquet, or this paper of Jiwano and Yehao Zhou. Jiwan is kind of a local; he's a postdoc at Oxford. What was I going to say? So, oh yeah, I should also warn you that maybe this is not the best prepared talk in the world, given I have, 2 young kids and not a huge amount of time for working these days. So normally when people study holography, they study some supersymmetric gauge theory. And how it relates to supergravity. But supersymmetric gauge theories often have a subsector preserved by supersymmetry. And in this subsector, things are easy. Maybe it's difficult to analyze the full gauge theory, but in the supersymmetric subsector, you can really do anything you want. So strictly speaking, preserved by supersymmetry means we choose Q, nilpotent supercharge, and we take the Q cohomology of the algebra of operators. So the question I want to ask is, what is the analog of this on the gravity side? Well, if you think about it, it's a little funny because in supergravity, diffeomorphisms are of course gauged. That's kind of the point of gravity. And in supergravity, super diffeomorphisms are gauged. And that includes these supercharges. So in supergravity, Q gauged. So Thiele and I proposed that the supergravity analog of this twisting procedure with something a little funny is to give a VEV to the superghost. So if you remember, when you want to study a gauge theory at the quantum level, you introduce fermionic fields corresponding to the gauge symmetry. But in supergravity, we have fermionic gauge symmetry as well as bosonic gauge symmetry. And the ghosts corresponding to the fermionic gauge symmetry are bosonic. This is a bosonic field. So the proposal is that the twisted supersymmetric gauge theory is holographically dual to supergravity in the background where superghost has a VEV. Okay, so I know this is, we've immediately gone into like things like ghosts and homological methods of quantization, and all feels a bit technical, but pretty quickly we're going to find that this twisted supergravity is actually quite simple, and we can just study it independently of its relation to the physical supergravity. Okay, any questions? No. I actually can't see anybody, I think, Mike, because the way this is set up, so it's hard for me to know.
People can unmute themselves, so they can interrupt. We're not such a large group that would create a problem. But please mute yourself again once you've stopped, once you've asked your question.
Kevin, is there interpretation on the physical subspace?
Sorry, it was on there. What was the question again?
If you go to the physical states without ghosts, is there an interpretation of this?
Yes. So normally, the way I would understand the physical states is you have a BRST operator and you take the zeroth cohomology. Now, on the gauge theory side, of course, when you're twisting, what you really should be doing is you add your supercharge to the BRST operator, and then you take the zeroth cohomology. So this is equivalent to what Witten was saying. And this ends up being, there's a spectral sequence, and this ends up being some subset related to some subspace of the physical states. On the supergravity side, well, even when you give the superghost a VEV, you should then take the BRST cohomology, and you find what you find. Does that answer your question at all?
Yes, thank you.
Just maybe I can ask as well. Just in the twisted SUSY gauge theory, how twisted are you? Twisting means that you are turning the fermions into rather trivial objects. You're moving away from the spin structure.
Well, right. So there's two aspects to twisting. So if you look in Witten's original papers about this, he emphasized that, because he's being a little loud, he emphasized that when you twist, you change the action of the spin group. But depending on, in a sense, that doesn't really do anything. You have the same field content, you've just relabeled them as living in different representations. And the other part of twisting is that you pass to a subsector by taking the Q cohomology per supercharge. So that's the part I'm emphasizing. And the second part really reduces what operators you find. Now, if you want the first part of twisting where you change the spin of the field, that can also be done in supergravity. This is quite standard. What you do is you work with, well, the global symmetry of the gauge theory is going to be related to Orr symmetry of the supergravity. So you give, there's a gauge field for the Orr symmetry group on the supergravity side, and you set that gauge field to be equal to the Levitt-Civita connection. That makes sense, Denjo?
Yes, yes, I know the one you're doing. But I mean, it has a physical difference because when you change the spin structure, you're turning the spinners into spin C or spin K, some larger spin representation,
but,
and they can have zero modes on a curved background when a normal spinner cannot. But there are physical differences.
No, there are physical differences, but on flat space, you just, were to calculate how many operators you have.
Yeah, no, I agree. Yeah.
It's the same number. They just live in different kind of relabeling which representations they live in. But yeah, absolutely. Whereas the second is passing to Q cohomology is a much more drastic change. It could get rid of all of the operators entirely. It could make your Hilbert space finite dimensional. So it's very different. Okay, so I'm going to be mostly focused on an example. We take the theory on n M2 branes. This is a 3D theory. With n equals 8 supersymmetry. So there are 16 supercharges. And there's, because it has so much supersymmetry, there's many ways to twist to get a supersymmetric subsector. But there's a particularly very nice protected sector where we have an effective one-dimensional quantum mechanical system. So the three-dimensional theory is reduced to an effective one-dimensional system. So there's two ways to think about this. You can think about this as a Nekrasov type omega background. Or there's this nice approach by Dean, this is over in Oxford, Rastelli et al., where you do a superconformal. So it's a little bit more general than what we discussed. There we take not a supercharge that squares to a translation, but one that's in the superconformal algebra, as of course analyzed by Werner many years ago. You take some appropriate element of the superconformal algebra, squares to 0, and this localizes your system to something one-dimensional. Now, what's great about this is that the theory on a bunch of M2 branes is very complicated. But the theory on this quantum mechanical system is really concrete.
This is the BFSS, or is it the BMN? Does it have a mass deformation?
For the M2 branes?
Yes. This projective sector is one-dimensional one. It must be either the BFSS model or the BMN model at the end, presumably.
I don't know. I'll write down the Lagrangian for you. I don't think it is either of those, but you can tell me. So what is the Lagrangian? So this quantum mechanical system has fields x, y, which are in GLN, I, which is in the fundamental, right, and j, which is in the anti-fundamental, right. And it's a topological quantum mechanics with no Hamiltonian. That's a little Lagrangian, but then we perform Hamiltonian reduction with respect to the GLN action. Or if you, let me say, let me use unitary notation. So these guys would be in U. And if you want, we can, I'm going to add on one more term, where A is the UN gauge field. We can add on this extra term if you want. This is a parameter which changes how we perform Hamiltonian reduction. This, we set the moment map to be equal to the identity instead of equal to 0. So when we do Hamiltonian reduction, the moment map equation is simply x, y plus I, j plus c times the identity is equal to 0. And you should recognize this is the ADHM equation. So this is not either of the models you mentioned, is it, right?
It's not. It's not what I expected. No.
Yeah, it's something extremely simple.
Yes.
So the point is, like as we were discussing, that passing through the supersymmetric sector, it kills a ton of the operators, and we find a much smaller collection of operators than you would have had in the original physical theory.
I think what surprised me is that your collection of M2 branes, you had some fields in the fundamental, and I'm not sure where they came from.
Well, they kind of drop out by the moment map equation. You can think about this. Well, one way to derive this is you work in a duality frame where you reduce along a tab nut to turn your M2 brane into a D2, D6 system. Now, you might be concerned that the size of the tab nut would matter, but for this twist, it actually doesn't. And in that case, the IJ fields are really like the D2, D6 strings.
Mm-hmm.
And more generally, if we had an M2 with a transverse to an AK-1 singularity, we find the same thing, except I and J are now bifundamental. For UN times, and then there's a UK flavor symmetry. Okay, so this is this is a really fun and simple matrix model. We have two matrices, two vectors, and we would like to understand this simple quantum mechanical system because no Hamiltonian. So what can we say about it? Let's work in the case with UK flavor symmetry. And we're going to take n to infinity. The algebra of operators is generated by the expressions which I'll call T, K, L, which is the trace I, X, K, Y to the L, J. So these are the analog of the single trace operators. There's one for every pair of integers. And I'm going to put in some flavor indices. So, okay. So, what are the commutation relations? Well, I'll write down some of them. So these guys form a copy of GLK. Whereas Bij10, so on these are in the adjoint representation. Of GLK. And there's some interesting commutation relations which you can just compute. For instance, we have Tij10, T or S01 looks like Ti or 00 T or J 00. Okay, so, and of course, you know, anybody who's studied quantum mechanics can do these computations. You know, the fields I and J are canonically conjugate, X and Y are canonically conjugate. We compute the commutation relations by reordering. We take these expressions here, we put them beside each other, and we reorder them using the canonical commutation relations together with the moment map equation, this moment map equation, and then we'll get some polynomial in these relations. So it's really quite concrete. Okay. So what I want to do is recover this algebra holographically. Okay, any questions about that? So the first question is, what is the holographic dual of this system? Well, so we saw that the M2 brane localizes to a quantum mechanical system. So we can think about it using Necker-Seltz notation. It lives on or2 epsilon times or, where this epsilon indicates we're equivariant with respect to rotation, and how fast we rotate is proportional to epsilon. And epsilon becomes some simple parameter in the quantum mechanics. So, well, the first thing we want to study is figure out what does supergravity become just on a flat space when we do the same thing. Well, the natural background for it looks like this. And here, my M2 brane will wrap these directions. And the corresponding localization of supergravity becomes a 5-dimensional theory, which has a nice Lagrangian description. And then what we're going to find is that by studying the Feynman diagram of this 5D theory, we can reproduce the same algebra. Okay. Okay. Any further questions? Everything okay?
I'm wondering if I take the M2 brane on that background, just as an M2 brane, using the supersymmetric action for it, and I do this Lycon quantization, like Jens Hoppe's approach, will I recover the action that you are dealing with, the one-dimensional action?
You should recover that action plus a bunch of very massive stuff.
Yeah. Okay.
So what's the point? So remember we were saying that, like, if I want to twist supergravity, I should give the superghost a Vev. Now, if you think about how supergravity couples to a brane, there's a term where, like, the superghost is coupled to the supercharge. So giving it a Vev adds the supercharge to the DRST operator. But I feel like one fun thing about this story is that even if you don't know anything about 11-dimensional supergravity, you know, the 5-dimensional gauge theory is much easier to write down than the 11-dimensional supergravity. So we can kind of forget the origin of all this story and just play with the 1D, 5D system instead of a 3D, 11D system. Okay, so what is this 5D gauge? Well, you know, in this localization, we've heavily broken it around invariance. So there's no particular reason it should be invariant under the group SO5, and it's not. So the 5D theory, it turns out to be a gauge theory. It is a field with 3 components. Let me write down coordinates R times C times C, T, Z1, and Z2. That the gauge field has AT, ET, plus AZ bar 1, DZ bar 1, plus AZ bar 2, DZ bar 2. This is a it's a GLK gauge field when we have an AK minus 1 singularity. So the AK minus 1 singularity should be here. So this guy transverse to the M2 brane. The Lagrangian is very simple. The trace there, trace ADA, plus the Chern-Simons type Lagrangian. And here we use Moyal product plus matrix multiplication. Let me explain. Let me explain the importance of the Moyal product. So for example, if k is equal to 1, we can write it like this. We're going to get factor of 1 over 3. Right, there's no trace because k is equal to 1. A del z1, A del z2, A plus expressions like A epsilon 1I2, epsilon J1, I2, J2, A del zi1, and sorry, I'm not having enough room. So what I'm trying to write down here is the Moyal product, the I1, but only in the only holomorphic group. Okay. So let me write out the first two terms a little more succinctly. Where here we see we're using the Poisson bracket. Okay, so this is slightly funny we're going in. So, and you might ask, what has this got to do with gravity? Like, why does it have anything to do with 11-dimensional supergravity? So let me try to explain how we might think of this system as a quantum mechanical system in the t direction. So if we view this as quantum mechanics with an infinite dimensional space of fields, then I think we should see pretty clearly how it has a gravitational nature. So there, the phase space is the space of 0-1 forms on C2. Here I'm sticking to the case k is equal to 1. I'll call this A. This is a natural symplectic structure. And we're going to perform Hamiltonian reduction by the algebra of Hamiltonian transformations on C2, where, so clearly this is kind of gravitational, right? Because we're Hamiltonian reduction by some diffeomorphism group, where the variation of A is equal to E bar X plus XA. So so if you view it this way, you can kind of see that this, viewed as an effective quantum mechanical system, this is the gravitational theory whose phase space is described by the collection of holomorphic symplectic. Okay, any questions about that? Or? Making sense, Tenjo, or?
I think that's reasonably clear.
Yeah,
maybe
okay.
people have questions. It would be good if people ask questions. Just
Yeah, it's just a little yeah. It's so hard when you're not in a room, right? The way I have this set up, I feel like I'm writing on a blank screen with nobody there.
yeah.
I think you can fire ahead, Kevin.
Okay. Okay, so this is the this is supposed to be the gravitational dual. So now here comes the tricky part. How do we connect the gravitational theory to the quantum mechanical system? But clearly, the gravitational system lives on R times C2, and it's holomorphic. It has a holomorphic nature along C2. That's because if we analyze the kinetic term, if we look back at the kinetic term here, I can rewrite this as the d bar operator. So the kinetic term is only d bar, and everything is entirely holomorphic. We only have z derivatives, no z bar derivatives in the interacting term. So on the other hand, the gauge theory has fields x and y. These clearly describe the motion of a brane on or in the normal direction. So by thinking about how the brane can be moved, we'll see that the gravitational theory and the gauge theory can be coupled.
Sorry, Kevin, I probably should have asked earlier, but the omega background in the gravitational sector, and you're dealing with 11-dimensional supergravity, so you've turned on some tree-form gauge field background. Is that how you've done it?
Absolutely right. Yeah. So so the 11-dimensional space, you can think of it as like a G2 manifold times or times. Sorry, not G2 manifold. It's flat space times or times C2, and we've turned on a three-form. But there's a very particular three-form for which there's a supercharge whose square is rotation in those three planes, and that allows us to reduce to an effective 5-dimensional theory.
Yeah, I have it. Yeah. Okay.
So I mean, in fairness, like it's very, you might ask, how is this related to 11-dimensional supergravity? Here we have some Lagrangian, 11-dimensional supergravity, you also have some Lagrangian. What you would like to prove, and which I have not done, but I've derived from various string theory arguments, but I haven't proved it directly, is that if we study 11-dimensional supergravity in a background where there's a VEV for the superghost and a certain three-form, we get this Lagrangian plus a bunch of massive steps. Now, that's not entirely obvious, not obvious at all, but you can derive it by thinking about how M theory reduces to type 2A with the D6 brane, and doing an omega and studying the D6 brane and the type 2A supergravity in an omega background. What you'll find. Okay. So here's the proposal, which is a bit odd, but actually works. That we can recover the operators on NM2s n to infinity as the Koszul dual of the operators of the gravitational system. So let me pause for a second, because as everybody knows, we do not think that gravitational systems should have any operators at all, because we're gauging diffeomorphisms that will move around the point at which you're considering placing an operator. Well, this is correct, but only for operators of Gauss number 0. When we gauge diffeomorphisms, we might introduce operators of positive Gauss number. And that's good because Koszul duality is an operation which is Gauss number 0 operators and Gauss number greater than 0. So even though the gravitational system has no operators with Gauss number 0, that doesn't contradict the fact that its Koszul dual does. Let me explain. I expect nobody's come across this notion. It's some kind of fairly well-known idea in the people who study homological algebra. It was introduced by Stuart Pretty in the 1950s, studying algebraic topology. I won't try to give you the kind of traditional math definition. I'll give you a kind of shortened version of that. So suppose too many things called A. C is an associative so a differential graded algebra, e.g. the algebra of operators of the 5D gauge theory, the algebra of local operators, where the differential is the BRC operator, and the product is equal to the operator product along the time direction. So, if one studies, for example, any quantum field theory in Lorentzian signature, and one takes the approach of algebraic quantum field theory, then any gauge theory in Lorentzian signature will give you an associative differential graded algebra. Then so the Koszul dual C shriek is a new algebra such that the following universal property from C shriek to B is any algebra this Hom is equal to the set of solutions to the Mohr-Cartan equation in C tensor B. So that's equal to the set of x in C tensor B of degree 1 with dx plus half x. Okay, so people should be kind of familiar with the Mohr-Cartan equation. It's a standard flatness condition. So we can ask, what is this? What is the meaning? I mean, physically. So if C is the local operators of the 5D system, and B is the operators of some auxiliary quantum mechanics, if I give you x in C tensor B of ghost number 1, well, it turns out this x, which satisfies the Markov-Stein equation, this is the same thing. I can't change the color. This is the same thing as ways as coupling the bulk theory to the effective quantum mechanics. So why is that? I take my x, and then I descend it. You get a one-form valued operator. X descended once, which is a one-form on OR. And then the integral over OR, x1, this couples the systems. And the Markov-Stein equation is the same thing as saying the quantum master equation holds for the coupled system. I won't go into details at this point, but you can kind of see, if I want to couple a gauge theory to some quantum mechanics, well, this part, since D is the BRST operator, so the thing I'm coupling by must be BRST closed to leading order. But if I work to higher orders, there could be contributions where the operator I'm coupling by collides with itself. This Markov-Stein equation is exactly saying that the coupled system is well defined, or gauge invariant. Okay, so they also spent the last few minutes. Okay, so now we've gone through a lot of materials. We have this 5-dimensional gauge theory, and we're saying, okay, I'll look at this Koszul dual of the algebra of operators, and the physical meaning of the Koszul duality then is of C shriek, that C shriek is the algebra so that a map into some auxiliary algebra, quantum mechanical system, is the same data as coupling E to the 5E theory. In other words, C shriek it's the universal algebra which I can couple to the 5D gauge theory. Okay. Is this very puzzling, or anybody make sense to you, Andrew? Or?
Yeah, I'm thinking about it.
Well, let me write it more explicitly. So how do we compute this guy? So it turns out that I have a gauge theory. I try to couple some quantum mechanics with some algebra. Let's just imagine the most general coupling and try to figure out what relations that must satisfy, and we're led to the Koszul dual algebra. So given B, what's the most general way we can couple? to the 5D theory. So there in the 5D theory, we have a 3-component gauge field. So the most general coupling, so the most obvious coupling is I can couple a T, I, J, some operators E, J, I. So that's the most obvious thing I can do. Given any gauge theory, I can try to couple some quantum mechanical system as long as that quantum mechanical system contains operators transforming in the adjoint representation. More generally, we can try to couple oh no.
You are insisting on just linear coupling.
No, so let me go back a little bit. So by dimensional analysis, I can only couple to something which is a 1 form along the T direction. But then you could say, why can't I couple to things built from AT and the other guys, AZ bar 1, AZ bar 2? It turns out you can't couple or I as the equations in motion say that the kind of the Z bar 1, Z bar 2 component of the curvature vanishes. So we can choose a gauge. This is one way to see it. Where the AZ bar I vanish. So in an appropriate gauge, it's clear we can't couple to them. Alternatively, if we don't choose this gauge, we can say R, the equations of motion say FT Z bar I vanishes. So coupling to AZ bar I will give us a total derivative. So that there's a few things to check that you can't actually couple to those guys. And then by dimensional analysis, we can't couple to squares of AT either, because that would be the wrong dimension to integrate over the line.
So you're insisting on dimensionless couplings.
Dimensionless couplings, exactly, yes. So the other way we get to dimensionless couplings is we get coupled to some derivatives of AT. And if you analyze, if you want those guys to be gauge invariant, you have to think a little bit, but you're not allowed to use Z bar derivatives. Well, see, that's not that hard. If you use a Z bar derivative by using the equations of motion, that becomes like integral del T AZ bar. So those guys go away too, by integration, because it's a total derivative. So the other possibilities actually no, no. Let's just make this argument with this gauge. The other possibilities are the integral of del Z1K, del Z2L, AIJ, EJI, KL. So this is, the most general possible coupling will look like this. So what we've concluded is that whatever this Koszul dual is, it's generated by elements E, I, J, K, L. And that's so if we map the streak B, then this derivative couples to Eij KL, the image of. Well, you probably don't recall, but right at the beginning so this is great because these match exactly with the single trace operators of the quantum mechanical system, which look like this. So there's a perfect match between the generators of this Koszul dual and the single trace operators. But now, if we look at some coupling like this one here, we've checked. What we've done so far to arrive at this expression is, does it look like it's gauge invariant modulo b squared? But now, to figure out the relations, we need to check, is it actually gauge invariant? So let me explain how to do this. And you end up. So here's my line. Here's my bulk gauge field, coupled like this. And I'm going to consider the simple case where I'm coupling with no z derivatives for now. So the coupling looks like the integral A, I, J, E, J, I. So this is going to be something familiar. Like, when is this coupling gauge invariant? And the answer is, it's gauge invariant if and only if the Bij satisfy the relations of GLK. So how do we see this? We vary A by a gauge transformation. Then this diagram here so we get a boundary term where these operators come together. And this boundary term looks like the integral. It's something that goes to number 1 because I have the x of the it looks like this. And this has to cancel with the term which looks like this. And here we have a bulk vertex. So if you analyze this diagram, then how this transforms under a gauge symmetry, we conclude that Eij, as you already know, must happen So this is the easy case. This is the one we already know. But it turns out that these simple commutation relations where the B's commute according to GLK require interesting quantum corrections. So let me do another example. And then I'll stop because then I'm running late. If we study this diagram, the gauge variation, you compute this using standard frame and diagram techniques, is the integral of Bij. I'm going to draw some indices. I'm going to write it schematically. This is the one which couples the things with no derivatives. And then so this, for this diagram to cancel, because we have these z derivatives, here, this must cancel with what you get from this diagram here, where my a's are coupled to things with derivatives. The gauge variation of this diagram gives you integral E10, E01, del Z1x, del Z2a. And by asking that the gauge variation cancels, we conclude that there's a relation of the form, sticking back in the indices, S 0, B, or J 0, 0. So this also holds in the quantum mechanical system.
Kevin, I can't hear you at the moment. Have you muted yourself?
Sorry, Kevin, I think we've lost your sound for some reason.
Oh, I'm really sorry. So this gives at least some idea that Koszul duality does indeed capture holography at the level of the algebra of operators. I'll stop sharing my screen there.
Questions?
I have a question. So C shriek is identified as this n goes to infinity algebra. But what else does it do for you? I mean, formally, does it stop you having to check some complicated gauge properties because you know they're true already? Or I mean, conceptually, what is it doing for me? I know I can see roughly what it's doing in this example, but
Oh, if I suppose that you weren't interested in holography, why would I study this algebra? What you're kind of thinking?
Yeah, but is there another example where you can see, oh, it must be expected that Koszul duality will help me here, so I'm going to just implement it?
Yeah, well, let's see. I mean, if you weren't interested in holography, what Koszul duality does for you is it answers the question, what line defects do I have? What is my category of line defects?
Mm-hmm.
What quantum mechanical systems can I couple? And the algebra you find, if you study this question, the line defects are always going to be representations of some algebra. And that algebra turns out to be very interesting in many cases. So if I was studying Chern-Simons theory, I'd find the quantum group. In a four-dimensional cousin of Chern-Simons theory, I'd find the Yangian or other infinite-dimensional quantum group. So, I mean, what to say? So this algebra is it's an interesting invariant of the quantum system, which captures the category of line defects.
Mm-hmm. Okay.
Some other questions?
May I ask a question?
Yes, please, Rodin.
So I'm just curious. Is there any kind of partition function defined for for the two sides so they match?
That's a great question. So this approach to holography only knows about the algebra of operators and doesn't know about the partition function. I think to give the partition function, you need an extra ingredient, which is a trace on the algebra. And if you think, the usual approach to holography, if I think, I maybe in this case, it'd be ADS4 times S7. So the algebra of operators only knows about what happens very near the boundary of ADS4, whereas the partition function knows about the entirety of the interior of ADS4.
Mm-hmm.
So that's not really present in this analysis. There's a recent paper of Davide Gaiotto and G10, who did, however, extend this to study the partition function. Their paper actually has graphs in it, which is far beyond anything I can understand. So they were able to get some pretty good numerical results.
Okay, thank you.
Some other questions? Maybe I can ask a more general question. I mean, what lessons do you think you've learned about holography from this? Just this is one example, but how general do you expect this type of holography to be? I mean, you've said it in the very supersymmetric setting. Many people try to use it far beyond that setting.
Well, I think the advantage of this setting is that you can get exact results. So the results we're finding here are exact, and it's all order. It's not just on this; it's all order in the loop expansion on the supergravity set. So that's something you're never going to find in a more physical system, because without supersymmetry, the quantum theory, I mean, it's obviously non-normalizable, and there's all kinds of ambiguities in fixing the counter terms of the supergravity theory. But here, I should have said this, even though the theory is also not power counting non-normalizable, you can use kind of BRST cohomology arguments to show that the counter terms are in fact fixed uniquely by the master equation. And then you can also use similar kind of homological arguments to show that the map is at all orders.
I mean, I appreciate that this is an example where you're establishing in some rather robust way that you have holographic duals to one another. But I'm more interested in, is there a lesson that I can learn for how to generalize it, when I might, do I need supersymmetry? Do I need all of this structure for to expect a holographic dual?
I have no idea. Yeah, I feel like well, if you look at just the quantum mechanical system we wrote down, that's a perfectly natural quantum mechanical system that many people have studied independent of any supersymmetry. And you could also give it, if you wanted to give it a Hamiltonian, that's easy to arrange. You can give it a Hamiltonian by turning on a Bev for a supergravity field, so that your copy of CQ has flows as you move along time. So I feel you could describe this without mentioning supersymmetry as an example of a toy model, a natural toy model of holography with matrix quantum mechanics.
Great talk, by the way, Kevin.
Thanks, Charles. I hope my kids weren't too disturbing. I think one of them had a little tantrum in the middle.
Oh, I didn't notice.
No, he's in tears. Maybe somebody else has a question that they want to.
Val, you nearly always have a question. No.
Werner?
No, thanks. It was clear enough.
Okay, very good. Well, let's thank our speaker again. Then, if we've no further questions, and I'll stop the recording.
Okay.
That's great. Thank you.
Thanks, David.